Hey there, Math 227. Here's something we either got to in class and it was fast if you're section 1, or we didn't get to it at all if you're section 2. And that is, if I have a matrix that has a complex numbered eigenvalue, let's find an eigenvector that corresponds to it. This is a basically purely mechanical exercise, but the way that I like to do it is significantly different than what's in your book, so I think it's worth me writing this completely out. Again, we went over this in section 1 this morning, but you might want to see it again, and in section 2 we didn't touch on this at all. So here we go. So here we have this matrix R. We found out that it has an eigenvalue of 1 plus I. There's also another eigenvalue of 1 minus I. Now let's do this here. Let's find an eigenvector that corresponds to this. Now to do this, we're going to need to solve an equation. And the equation is A times X equals 1 plus I times x. I need to find a vector, a non-zero vector, such that ax equals 1 plus I times x. Now, it's kind of strange to have a complex number right here, but if you think about it, this is the same equation we always solve when finding an eigenvector. We're just looking for a non-zero vector that satisfies the equation that is in the definition of eigenvector. The one twist here is this presence of complex numbers. We have a complex number in the eigenvalue, and also x, the vector here, is in a space called C2. C2 is like R2. It's a set of vectors with two components. The only thing is here that C2 is a set of vectors with two components where complex numbers go into the components. Okay, so for an example, a vector in C2 would be something like I plus 1, I minus 3. Okay, that's a vector in C2. So I'm looking for a vector in C2 that satisfies this equation. Let's just kind of walk through this, and what I want to emphasize is every step of the process here, with a couple of exceptions, is going to be exactly the same process as when you're finding an eigenvector that corresponds to a real number eigenvalue. So hopefully a lot of this will look familiar. What I'm going to need to do first is subtract the 1 plus I x from both sides to get this equation. Ax minus 1 plus I x equals the zero vector. So I'm looking for a non-zero solution to this homogeneous equation. Now what we normally do at this point is factor out the x, and that's going to give me A minus 1 plus I times the identity matrix. So there's two instances of the letter I on the screen now. One is the lowercase I, and that's the square root of -1. The other is the uppercase I, and that is the identity matrix. So here again, I need to think about what is this matrix right there. Okay, so finding non-zero solutions to a homogeneous equation is all about thinking about the coefficient matrix here. So let's write out what that coefficient matrix actually is. I said A up here. I was using the letter R. Let me just go back and retrofit that and call that A. Okay, so A is the matrix 1, 1, -1, 1, minus, and I'm going to subtract off 1 plus I times the identity matrix. So I'm going to have a 1 plus I there, a 0 there, a 0 there, and a 1 plus I right there. I'll do a little arithmetic here, and you can check some of the gaps here. This is going to give me the matrix -I, 1, -1, -I. That's an I right there. So that's the coefficient matrix here. Now what we normally do is we are going to, this is this, in other words. So now the way we solve these homogeneous equations is the same way we solve any equation. I'm going to set this up in a augmented matrix and then row reduce. So let's do that. Let's take this equation here and write it as its augmented matrix. Okay, now the twist here is that there are complex numbers everywhere, but let's just kind of ignore that for now and write what we think we should be. So -I, 1, and here I'm going to augment with 0, 0 down here, and then -1 times -I. Now what I want to do is the exact same thing that I do when I have all real number entries here, and that is row reduce this matrix you see here to its reduced echelon form and grab the general solution to the system. And we're still going to do that. The only twist here now is that when I do a row operation, I can include complex numbers in any scalar that I wish. Okay, so for example, one thing that I'm going to do right now is do a replacement. I would like to zero out this -1 right there, and I can do that if I do the following. I'm going to take row 2 plus itself times I times row 1. So I'm replacing row 2 with itself plus a scalar times row 1. That scalar happens to be the number I. It's going to be helpful to think about what is I times row 1. I can do that right up here, actually. So if I take I, the square root of negative 1, times row 1. Okay, row 1 is negative I, and then there's a 1 over here. Okay, what is that? Well, in the second component is going to be an I, obviously. Sorry about that. I'm going to take I times 1. And in the first component here, it's going to be negative I squared. Okay, let's pull this down here because I keep hitting the forward button on my slides. What is negative I squared? Negative I squared, let's see, that is negative I squared. I squared is negative 1, and so that is 1. Okay, so when I take I times the first row, I'm going to get 1I. And that's what I'm going to add on to the second row. Now notice the second row is negative 1, negative I, so this is pretty convenient. That's going to give me this matrix. It's going to give me negative I, 1, 0, 0, 0, 0. Okay, if I encourage you to pause, rewind, and especially work that out yourself if that didn't make a lot of sense right now. All I'm doing is multiplying scalars around with the twist that I squared is equal to negative 1. Now what we need to do now is get this, so this matrix is now in echelon form. What I need to do is get it into reduced echelon form, reduced row echelon form. I'm going to do that on the next page here because we're running a little short on room. So let me rewrite where I was. I was at negative I 1 0 0 0 0, and I just need to get this into reduced echelon form. And I can do this by rescaling the first row by a factor of I. Now what that's going to give me here is negative I squared and I and a 0, and nothing happens to the second row there. Negative I squared, as we saw earlier, is equal to 1. And I have an I right there, 0, 0, 0, 0. Okay, so now I have enough ammo here to write down what the general solution actually is. Okay, what we see here is that I've got two variables, x2 and x1. x2 is free, and x1, according to my top row right here, is equal to negative I x2. Okay, so if I want a sample solution, well, let me write out the general solution in parametric vector form. The general solution would have the form x equals x1, x2. X2 is free, x1 is negative I x2. So I have this, and I only pull out the x2 factor, and I have negative I1. Okay, so this vector negative I1, notice this belongs to that space C2. It's a two-dimensional vector with complex number entries. If I wanted a sample eigenvector, then I could just choose x2 to equal 1, for example, and so one particular eigenvector for the eigenvalue 1 plus I is the vector negative 1I. Now, just to prove that this is the case, and this is kind of an optional step, but I think it's important to do, let's multiply A times this vector here and see what we actually get. So I'm going to do that over here. Now, A times X, okay, that is the matrix is 1, 1, minus 1, 1. My X was negative I, 1. And now let's multiply through. That's going to give me negative I plus 1, and then on the bottom it is I plus 1. Now, what is 1 plus I, on the other hand, times x? We hope these things are equal to each other. So let's find out. 1 plus I times x, that's this vector here, negative I, 1. Well, on the bottom, things work out really nicely. You can see in that second component, I'm definitely getting 1 plus I, and that's the same as I plus 1 in the top row here. On the first component, I'm going to have to do a little bit of scratch work. 1 plus I times minus I. Okay. Now let's just move down to the bottom left here and work that out. What is minus I times 1 plus I? Well, let's just multiply through. This is a negative I minus I squared. We've already seen that I squared is negative 1, and so I have negative I minus a negative 1, which is, so I can see if I do a little simplifying here, this is just going to be 1 minus I. And let's put that back up into my first component up here. Let's see what we got. 1 minus I, I'm going to write that as negative I plus 1. And on the bottom I have I plus 1. And just notice that these two things are indeed the same. So that vector x is really an eigenvector for the complex number eigenvalue I plus 1. Now notice again the eigenvector is a complex numbered vector. It's not a real numbered vector. There won't be any real numbered eigenvectors if you have a complex eigenvalue for reasons we discussed in class. But that's the procedure. The thing to note is that it's the exact same procedure as you've been doing for finding eigenvectors since forever, since you first learned eigenvectors and eigenvalues. The only twist here is that you get to use complex numbers sometimes. Okay, so I hope that makes sense. Rewind and replay and do some more examples on your own to make sure that you understand this. Thanks.